Hello everyone. In this video, I'll be talking about this paper titled Critic-Regularized Regression. The authors are Ziyu Wang, Alexander Novico, Konrad Zollner, Josh Tobias Springenberg, Scott Reed, Bobak Shahriari, Noah Siegel, Josh Merrill, Kagler Gulcheri, Nicholas Hayes, Nando de Freitas. I apologize if I messed up some pronunciation, but yeah, this work was solely done by Google researchers. So yeah, let's go ahead into the abstract. Yeah, as you can see, this is work on offline reinforcement learning, uh, which I mean, recently I've been covering many videos covering all these offline reinforcement learning works. So this is an addition to that. Mhm. So yeah, as we have already seen, offline reinforcement learning offers a prospect of policy optimization for working with the large data sets instead of interacting with the environment. So here it addresses the challenges with regard to cost of data collection and safety. Yeah, these two are the important aspects of this offline RL, which helps to utilize already available data to come up with good RL algorithms. Um, yeah. Yeah, most of policy algorithms which already exist perform very poorly in this setting. So it offers a good space to develop new algorithms in this area. So yeah, mm, yeah, this paper proposes an new algorithm named Critic-Regularized Regression. So yeah, and they also test on various state-of-the-art benchmark. Yeah, I mean benchmarking state-of-the-art offline algorithms against many benchmark tasks. So yeah, now we move on to the introduction. So this is the usual introduction in all of these offline RL papers. So first um, tell what the online RL problem is about. I mean, what are the challenges which can be elevated in the offline RL part. So online RL is not feasible for or desirable because of the cost, safety, and ethics, which are like elevated in the offline RL part. So yeah, that is the first motivation. mm, yeah, so the RL involves a close interplay between exploration and learning from experiences, which makes it difficult to compare different algorithms. By separating out these two problems, it becomes possible to share datasets with benchmarks. And yeah, one could also leverage already developed methods from supervised learning, because supervised learning also depends on the large data set without any interaction with the environment. So that is one possibility. And yeah, elevating exploration, one can focus on just optimization aspect in the exploitation part. So yeah, the naive application of policy RL. Yeah, so the present existing algorithms of policy algorithms like Q-learning and so on doesn't scale to offline RL, and it is shown in various papers that it fails. Hence, yeah, I mean, one of the extensions of Q-learning is BCQ, yeah, which this paper also mentions, which I'll talk about in a few moments, which solves this offline RL problem in a particular way. So yeah, that is one of the state-of-the-art offline algorithms which they compare with as well. So yeah, stay tuned for that. Yeah, some challenges are mentioned here. So optimistic Q estimates and as well as inappropriate extrapolation beyond the observed data. So yeah, in the previous videos and previous papers actually give a few keywords to these. So optimistic Q estimates for an unknown state action pairs is named as overestimation, and inappropriate extrapolation beyond the for the distribution which has been not been seen in the from the data set is called as distribution shift. These two are the main challenges in any offline RL algorithm. So yeah, uh, yeah, this picture is like a TLDR for this paper. So it summarizes what CRR is actually aiming for. So let's pass this through. Yeah, the task is to reach the reward from starting position as fast as possible to the goal there. So AT-ST is the pair of from the batch. Pi of ST is the current policy. So AT coming from the batch is used for training if the value it provides is greater than the value the policy action is providing, and you discard those actions which is otherwise. So that is colored red. So yeah, so CRR, that is like summarized here. Yeah, so CRR filters out bad actions and enables learning policies from low quality data. So this somehow captures the high quality, and this is like low quality data. So this will be captured in some sense of distance metric. So stay tuned for that. Yeah, I think that is the TLDR for this CRR algorithm. So let's move ahead. Yeah, so Q actions is queried for actions that were not observed where errors can accumulate. So yeah, so this covariate shift is was done in behavioral cloning. So yeah, so in this paper we propose in so value fitted regression that requires minimal algorithm changes to the standard actor critic. So CRR is an actor critic method. So that is yeah, that is decoded from this paragraph. So yeah, that is model free. Yeah, so now despite apparent simplicity of CRR, outperforms several, okay, and it scales to tasks with high dimensional state and action spaces, and does well with data sets of low quality data as well. So I've already passed through this paper once, so that the video is shorter in length. So yeah, a comparison with model based RL algorithms would be one of the good things to make, because in the previous few videos I reviewed two papers, MOPO and MOReL. So both are model-based RL algorithms. So and they claim that MOPO actually shows that in few instances model-based RL outperforms model-free RL. So yeah, so that would be a good comparison to add as well. So now we move on to the background or the literature survey. So let's dive into this. So if if you want to deep dive into this offline RL literature, then yeah, these two references are really cool. You will need to check it out. Yeah, I've just pointed out I think there is some grammar structure mistake here in this statement. So yeah, if you catch on to this video, please correct it if possible. Yeah, so now we move on to some of the related work. Like yeah, the first one is the imitation learning part, which is behavioral cloning. So yeah, even this behavioral cloning is also applied on offline is an offline learning, but here behavioral cloning assumes the offline data is actually high quality data which is coming from an expert. So most of the literature goes into making your algorithm perform as good as this data. So yeah, so it can easily fail when the dataset contains large proportion of random some suboptimal tasks, and when the learned policy includes a trajectory distribution that deviates far from so a distribution shift. So even behavioral cloning suffers from different I think there, since the error accumulates if you go on to the wrong path, that terminology is called covariate shift. So I think it comes under the same umbrella of distribution shift. So yeah. So the next paragraph, offline learning, offline deep RL. So which we talked about like Q learning. So let's see. Unlike BC, these methods have advantage of reward functions. So the interaction with the environment is possible. So that is one difference between that and offline RL. So a recent paper, Fujimoto, corroborated that distribution variance by themselves can be. So they designed BCQ, which is in this reference 10. So yeah, so here to give you a big picture of BCQ, it's so in Q learning you update the target Q update is over all the action space. Over the full action space. So here you just restrict your action space by some sort of distance metric between the data set and the current policy. So the current data set is used to generate this model. So yeah, you use this distance metric to do so. So yeah, going into more details. So one line of work focused on constraining, that is what the BCQ does, and many others have been proposed. You can check out these references. So yeah, let's see another line of work which is called weighted behavioral cloning. Okay, let's see. The idea is to estimate the advantage function to select best actions. Okay, so this kind of does choosing between chooses best actions in the suboptimal data set given. So that is one way. So examples of this approach include monotonic advantage reweighting and ABM. Yeah, I guess these are the algorithms which can be compared with. Yeah, so CRR differs in one way because they don't have interactions between the environment with the environment, so that is what this means towards of an NRL. So additionally, we introduce a technique we call CWP. So yeah, that uses learn critic to improve the results at a test time. Yes. So let's go ahead. Yeah. I think they mention about filtering here. So filtering component in CRR. So what I understand from filtering right now is from the data set itself, you try to pick better actions. So that can be done in various ways. So one has to go read these papers, I guess. So yeah. So now, for now, in this video, I'll stop by discussing about this filtering. So indeed, our analysis in section 4 demonstrates design elements such as sample efficient estimate for binary and exponential filtering. So two types of policies are looked at: policy improvement with CWP. So they actually prove that it improves. So carefully designed deep recurrent networks, dramatic difference in quality results. Yeah, so this is the practical implementation. So let's go ahead. So here I think the background for CRR is given. So yeah, let's directly jump into this. So the first step is the policy evaluation. Suppose we are given the fixed data set B. I think this is just to keep it simple. The this same algorithm can be extended for k-step trajectories part. So yeah, we'll keep it simple in this thing. So it's a tuple of all these variables, the current state and the next state with the reward as well. So yeah. So let's see, an important step of many offline approaches is the off policy evaluation. So given a policy pi, we need to evaluate the average return. Here it's the discounted average return. So yeah. So yeah. So basically in any Q-learning algorithms, you try to approximate the current model Q theta with the target model, which is given by this expression. Usually in Q-learning algorithm, this is an L2 loss, L2 in Q-learning. So this is provided for generality purpose. So so D is some divergent measure, Q theta is the current estimate of the action value, and the TD update based on the target network Q theta prime. So you know that we make distribution on Q function as in Barron, Barth-Maron, instead of using squared error. So yeah. So as discussed in the recent work, without interaction, due to bootstrapping issues mentioned above, where we evaluate the next value using this So yeah, this is the distribution shift issue. So yeah, if trained with the standard RL, yeah, we face with this extrapolation or distribution shift issue. So yeah, for these actions Q that will not have been trained and may produce bad estimates. So yeah, the motivation for BCQ comes from here. So the set puts a constraint on the such actions as well. So now policy update step. So let's see, to mitigate aforementioned problem, to avoid evaluating Q from SP, we have to aim to train the policy by discouraging and taking actions that are outside the training distribution. Yeah, so such a requirement would be hard to achieve using, okay. We'll see later that the dataset policy mu b for this pair SA is proportional to the number of times you have seen this pair in the dataset. So this is why it is Markov, and it is stationary as well. So it is sitting inside this red set, and then proposition 1 shows that this green set is a subset of all these dataset policies. So this green set is where the current policy pi will concentrate on. So yeah, this is the structure of the policy space. If I made any mistake or if you have any comments on this, please feel free to discuss in the comment box. So yeah, I just wanted to add that like most of the offline RL setting, this dataset policy might contain non-Markov policies as well. So this set might extend outside the red box, the red set as well. So which is, I think, is not addressed here. Maybe that is not an issue. So let's go ahead with the with the formulation of this paper. So I just had this point in mind. So so here the f of q might be anything like advantage function, or we'll see later what that is. So basically you need f to be non-negative scalar and function which is monotonically increasing in q theta. So yeah, so equation 2, as I said earlier, is trying to copy actions that exist in data, thereby restricting pi. So yeah, this might first look as it is conservative than BCQ, but as we'll see later, it is more or less doing similar things in a unique way. So yeah, it might not be conservative than BCQ. I had 3 more points here, so let's discuss it. So maybe better at handling overestimation. So unless we characterize this overestimation, which this paper does in the appendix part, so it is actually handling it better. So and the analysis follows from BCQ paper, so which I'll look at in this video, so stay tuned. With this large data set, we can reach the optimal return. So but it's an asymptotic result. So as MOPO or MOReL give some characterization depending on the dataset size. So you can't really say for sure how good CRR will work compared to MOPO or MOReL with the suboptimal dataset. So, and the third point will be, yeah, a question that will it be better than dataset policies? So the policy pi which we learn, will it be better than the dataset policy? I mean, that is the usual aim in this offline RL setting. That is, it is not sufficient if you reach the performance of the performance of what your dataset policy is promising. You have to like exceed its performance. So yeah, uh, yes, CRR does. So it, I mean, the big picture of how it does is uh, mixing up the suboptimalities of all the policies, which yields the better performance. So which we'll see in the evaluation of this paper. So yeah, these are the few points which I had in mind. So here is the algorithm CRR, the pseudo algorithm. So the inputs are dataset, the net q theta, empty q theta, and actor net, and the target nets, which are the copy initially of these things. So now during the update, sampling from this one, and the actor update is done by equation 2 loss. You can see the gradient written here corresponding to equation 2 above. And this is the critic update, which depends on the target. I think it follows from this equation 1. So yeah, you just update the target actor nets once in every n steps. So yeah, that is the simplest explanation of this pseudo algorithm CRR. Yeah, let's see further. So if f is 1, denote that equation 2 is very equivalent to behavioral cloning. So yeah, this part, right? So f is 1, so it is just taking care of the it does not considering this term at all. So yeah, it is only considering this because behavioral cloning things pi is behavioral cloning things, this data set is expert policy, so it is trying to reach that part. So yeah, that is what I have summarized here. So quality of dataset B. So yeah, so in the CRR they actually concentrate on these two variants of F. Yeah, intuition wise, I don't think I have one, but let's see. Let's see if we can bring out some aspect of these two things further. Yeah, let's see. So beta is the hyperparameter. So a theta is the estimated advantage function, which they mention in the table 1 here. So CRR is using both of these things, and other offline RL state-of-the-art algorithms are also mentioned here. So yeah, so brief description about these things are like mentioned here. So filtering increases average quality of the actions we learn. So the filter is defined in terms of value of the current policy. So yeah, so this is the definition of what filtering is. So yeah, restriction with respect to the data set, the current policy is being filtered. So yeah, so let's go ahead with this policy iteration step, exponential weighting. So here you can think of the parameter beta. Whenever it is 0, then this term won't exist. So it's like concentrating on the traditional of policy RL algorithm, which so considers the whole space, whole Markov space, which has this overestimation challenge which we talked about. And when this beta goes to infinity, it is similar to behavioral cloning, because you are trying to approximate your policy. I mean, your policy should lie very close to the dataset policy, which is only, I mean, which only makes sense when your dataset policy is coming from an expert. So here CRR, what it does is try to choose the best beta, which is nothing but staying in this green region which I showed earlier. So here these Q policies are the soft max kind of policies, so which is coming from this equation 4. So yeah, this is the summary of this paragraph. Let's go ahead. Theoretical analysis is provided, which we will also look in this video. So let's go ahead, finish this section. Yeah, I think I'll just pass through this few statements here. I don't have any intuitions or any additions to this. So yeah, let's see. Consider a mean, but found that small m, which is the number of samples which is averaged upon, it may overestimate. So yeah, this follows on the classical central limit theorem. So they also consider a max, which is the pessimistic estimate. So yeah, the convergence guarantees also are weaker for max, and so it should work better. So yeah, so here they mentioned AWR, which uses this so Monte Carlo version of estimation of our advantage function. So yeah, these are different estimates for advantages which one can use. So I think these will be presented in the evaluation section. I've forgotten, but yeah, let's go ahead. The choice be fine to not work well in many offline RL scenarios. Okay. A full listing, okay, in one. That is the table 1. Yeah. CRR versus the return based methods, which is the AK and AMC. Let's see, they are providing an example here, so I'll try to explain this as well. They give an example of two-armed bandit problem. So the first arm is the fair arm. It switches between values 0 or 1 with probability 0.5. So the average payoff would be 0.5 as well. But the second arm, which is the deterministic arm, so whenever you pull this, you will always get a reward 0.9. So the optimal arm would be the second arm. So that is why I have called it as mu star. So let's assume the dataset, any size of dataset, but the ratio of this dataset is such that it contains 2/3 of its data to be coming from this arm1 and other 1/3 to be coming from this arm2. So now if we calculate the ideal q star values, since the state is 1 here, I have removed that. So this variable is an action, so the q star of this first arm would be just half and q star of the second arm is 0.9. So because that is the return value, and so that is why it is written here that q function will clearly favor the arm2 over arm1, but when you use advantage estimation, which is r minus v or r minus q here, so the signs flip, and so regardless of any temperature parameter beta, it is preferring the first term. So yeah, that is the disadvantage which is faced by this return based algorithm. So yeah, let's go ahead. Yeah, the CWP is the last part, which is used in improvement of the policy. Yeah, here it's like doing an important sampling. So given so let's write this. You know you want to sample from q bar here, this part, but you know the current policy pi phi, so you are sampling from pi phi to look like a sample which comes from q bar, which is done by multiplying this weights, which is coming from this expression here. So yeah, this is very similar to what importance sampling does. So which elevates the problem of calculating this z of s expression here, which is the partition function, which would be a messy expression to evaluate. So importance sampling is one of the methods to come over this problem. So yeah, that is the gist of what CWP is. Now before moving into the experiment section, we'll move on to the appendix section, which provides some analysis for this CRR algorithm. So let's move ahead. Yeah, I'll be like pretty fast passing through this section. So our model is built, the transition model from the dataset, the usual empirical method, and the policy MOB as well. And this is the distribution of the states. You actually have state action visitation frequency, so here it's just state visitation frequency. So the q value is built upon this data set using this expression for any policy pi, and the normal the value function, which is the expectation of the q function. So since you are considering the softmax policy, so yeah, so here the expression 4 implies what the policy update would be in this fashion, where it's the KR divergence which is used in place of D, and the expression 3, which we saw that f is the indicator function, where you just pick the best q. If the q of that action exceeds the value, so this is how your I think this expression 7 is very close to the figure 1 which we saw for explaining the CRR using a TLDR statement. So yeah, so now we consider only this expression 6, and the similar analysis would follow for this expression 7. So yeah, so now the closed form solution for 6 would be 8, which follows from the KKT conditions. Yeah, so Z is the normalization constant which we saw earlier. So this is the one which CWP is avoiding. So let's go ahead. So in the tabular setting where you have finite states and action space, we saw that the support of the policy is a subset of the support of the dataset policy. So yeah, which we saw earlier as the green and the blue curves, blue sets earlier. Yeah, the sets which I showed was actually covering the policies. Here it's the support. I guess you could make it equivalent, but yeah, I'll neglect that. So for simplicity, yeah, the important result is this proposition 2, which is the policy improvement step. I would like to pass through the proof as well. So let's see. So here the second part is considered. So for the other part, it's really very similar to how this analysis goes through. So yeah, we are considering this equation 7. So let's go ahead. So you define Q as this, and from 7 we have this pi I plus 1 policy. Yeah, this is by definition, and this is from the above definition Qi plus 1, and so pi I plus 1 will eventually turn into this using the KKT condition. And yeah, so from the above equation it is easy to see that for all a in the support of this pi I plus 1, yeah, for us, because of the indicator function you have this condition. So yeah, and therefore you can write it in this way, the expanded form. So yeah, let's see. So here this first line is the definition. I think this is a typo. It should be t plus 1, I think, but yeah, let's see. Yeah, from here, yeah, so star is applied here. So yeah, pi I plus 1 is pi I will change to pi I plus 1, and from here to here I've tried to pass through this. Let's see. So this expression can be expanded using the bootstrapping method. So this expression, this quantity can be replaced using this thing. So we have a recursive expression here. So this can be pi plus 1, pi I plus 1, and further bootstrapping you would get this part, and using the tower property, because you have two kinds of expectations. So yeah, these are all hand baby, but yeah, you could more um, formalize this using the filtration method. So yeah, you could avoid that just for simplicity. So yeah, doing this for all the cues which exist here, and uh, see that this is a probability value which takes the maximum value 1. So thus here is upper bound, and this is just the discounted average which you would get here. And finally, this is the q value, which is the original definition. So yeah, just adding one more statement here. So this definition comes from the Bellman equation, and this is the original definition of the q value. And so you have improved your q value from moving from pi I to pi I plus 1. So you have improved your q by I increases. So this is a short statement. So similar proof technique for the other part, the equation 6 would be here. Yeah, as you can see, it's still repeating of the earlier statement. So yeah, another important result which is mentioned here is of that the distribution shift. So you can see BCQ paper theorem 1 for more details. So this is a short version of that. So epsilon MDP defined by this quantity. Here this is the true Q for a policy pi, and this is a Q which comes from the dataset policy for any which comes from the dataset, but for any policy pi. So yeah, this is the distribution shift. So yeah. So finally, to conclude, as this data set increases to infinity, I mean the size of it, then the epsilon MDP of SA, which is the distribution shift across the state and action pairs constrained here, goes to 0. So in short, it is saying when your data set becomes larger, the optimality gap is going to 0. So yeah, from the BCQ paper, gamma 1, you have this epsilon MDP recursive expression. So here the P subscript M is a true model. So and PB is the model which is created earlier, which I have shown. So now let's get into more details. So since B is coherent, the value functions are like limited to the S and A pairs among these sets. So you could just upper bound these terms with its supremum value. So that is why you're going from here to here, and then you would just take sup on both sides. Now you have the same terms, this and this on each side, and so you would end up getting this part which is saying you are far from your model, and with this gap. But yeah, so they use a result from one of the papers which in short says this. So your L1 distance between the distributions of the true distribution and the empirical distribution goes to 0 as n increases. So that is what they're using here. But I have a question. Does this result hold for any policy? So that question is I'm asking because so this dataset based model, which is built from the dataset itself, is coming from the dataset. So yeah, but that dataset can be collected using suboptimal ones. So don't know if increasing the empirical size of that dataset would approach this PM, or I guess this result holds when the dataset policy is actually the optimal policy. So I think I can believe that statement, but this might also be true, but yeah, I have a doubt of applying this result of theorem 1 from 11, which only says this, but not for any pi. So yeah, this is one of the issues, I guess. But yeah, I think this can be elevated because BCQ paper also does this analysis, and there might exist some nuance which I haven't seen. But yeah, please comment in the comment box if you have any insights to this question. So yeah, let's go back to our main content of the paper. I just wanted to present this appendix result so that one can easily go through the analysis. Yeah, so let's go ahead. Let's go back to the evaluation section. So yeah, the experiments, so high dimensional actions are considered. So these are from the DeepMind control suite, so it's not the normal gym environment. So yeah, if you see this box, CRR actually does really good in various environments compared to BCQ, ABM, and I guess BC and D4PG are not especially designed for offline RL, so they would just perform lesser compared to ABM and BCQ. But surprisingly, as you can see, ABM is not, D4PG is actually better in these first 6 environments rather than the last 3, which are hard. And yeah, you could see that ABM is actually performing better than behavioral cloning and D4PG. But CRR is good, doing almost better than anything else in all the environments. So this is a good result. So one could extend results from CRR. So yeah, as I've said earlier, it should be interesting to compare with MOPO or MOReL. Yeah, and yeah, the important question would be like, would this high dimensional action set be a problem for model based RL? That's the question. Because I've seen MOPO and MOReL also solving locomotion kind of problems on Muzoko environment. So yeah, it would be an interesting thing to just check it out. Let's go ahead into the setting of the experiments. So DeepMind control suite is used. So dataset consists of both successful and unsuccessful episodes. Are relatively straightforward. Yeah. A number of these tasks are quite challenging with high dimensional settings. Yeah, locomotion. Yeah, I guess these are the three humanoid tasks. Avoiding obstacles like walls, gaps. Data of these tasks are generated by training a hierarchical architecture. So pre-trained control for generating dataset, but not enough. For the rodent environment, there are 4 tasks comprising escaping, foraging in the maze. So yeah, good diverse data set is being used. And high dimensional access, 56 dimensional space, 38. This is quite extensive, so nice. That's quite robotic manipulation, agent to control, solve number of manipulation problems, 2 camera views. So yeah, this is really high dimensional environments. So I guess this is where model free algorithms like CRR would be, I mean, really work better than all the model based settings. So yeah, so they also consider, even in this table I think CRR is performing better than anything else. Yeah. So the architecture sizes are given here. So it's a really complex setting of the neural architecture. So yeah, I guess you would need this amount of complexity to solve the high dimensional setting of the environments. So yeah, this is a really cool set of experiments. So yeah, yeah, as you can see here, we use resonance to process the visual inputs. Critic and policy networks share vision modules. Yeah, just to process the states and action spaces. So crucially when evaluating CRR, yeah, we turn off noise in the course. So I guess these are the practical tricks to compare with the state of the art of NRL algorithms. So yeah, CRR versus architecture from 14 found later to be superior. Okay, yeah, so D4PG is not good. So let's go ahead. So interested readers of CRR can use this section for trying to extend trying to come up with new offline RL algorithms. So yeah, this would be really cool. I'll just end this video by discussing the conclusion. It also mentions one of the important future work. So here it is. So given the already promising performance of CRR, we believe studying of underlying dynamics further is a valuable direction for future work. So yeah, approximating μb in a new way would be one of the directions to move in. So yeah, and the constraining the target update would be one other variant. So yeah, which can add robustness and so on. So yeah, and a broader impact would just add that the existing data set to be non-biased. But I guess all the like the data sets which are available in power systems, and those won't have these issues. Yeah, so yeah, I think that this is the end of the video. So if you have liked this video, please watch the other stuff as well, so that you might like it. So yeah, just to end this discussion, please comment anything relevant to this paper, and yeah, I will be happy to reply to the comments as well. Yeah, take care.